Hello there, and welcome to the Sleepy Library. It's lovely to have you here tonight. Before we begin our gentle journey into the impossibly small, I'd love to know where in the world you're relaxing right now. A cozy bedroom with soft pillows, a quiet corner with a warm blanket, or perhaps a peaceful space where you can finally let your thoughts slow down. Wherever you are, I hope you're comfortable, safe, and ready to explore one of the most beautiful mysteries of our universe. The world of things so tiny, they make a grain of sand look like a mountain. If you enjoy these calming explorations of science and would like more of them, a like and subscribe really helps this sleepy little channel grow. And to those of you already subscribed, thank you from the bottom of my heart. Your support means everything. Tonight, we're going to explore something extraordinary. Something that exists all around you, inside you, even in the air you're breathing right now. We're going to explore atoms. These impossibly tiny building blocks that make up everything you can see, touch, taste, and smell. And I promise, I'll try not to make it so fascinating that it keeps you awake. Though, if it does, at least you'll drift off knowing just how wonderfully small and perfectly constructed our universe really is. So settle in, close your eyes if you'd like, and let's begin this gentle journey into the microscopic universe. A place where nothing is quite what it seems, where emptiness is full, and where the smallest things create the biggest wonders. Let me ask you to imagine something for a moment. Think about your hand. Right now, in this very moment, your hand exists as something solid, something real. You can feel it, move it, touch things with it. It has weight and shape and presence. You can curl your fingers into a fist. You can spread them wide. You can feel the warmth of your skin and the slight movement as blood pulses through your veins. Your hand feels completely and utterly real, doesn't it? Solid, dependable, there. But what if I told you that your hand, this solid thing you trust completely, is made of particles so small that if you lined them up side by side, it would take 20 million of them just to measure a single millimeter? What if I told you that between these particles, there are vast stretches of empty space, proportionally larger than the space between planets in our solar system? Your hand, which feels so solid, is actually more empty than full. It's a collection of tiny specks separated by enormous distances, at least on their scale. This is the world of atoms, a world that exists far beyond what our eyes can see, beyond what any ordinary microscope can reveal. It's a world measured not in centimeters or millimeters, but in something called nanometers. 1 nanometer is 1/1000th of a meter. That's such a small number that it's hard to grasp. Let me try to help you understand it. If you had a meter stick and you divided it into 1 billion equal pieces, each piece would be 1 nanometer long. If you tried to mark those divisions on your meter stick, you couldn't see them. They'd be far too small. You'd need thousands and thousands of them just to make a mark visible to your naked eye. To put that in perspective, if a marble were the size of 1 nanometer, then the Earth would be the size of 1 meter. That's how vast the difference is between our everyday world and the atomic world. The scale is so enormous, the jump is so dramatic, that our brains struggle to process it. We simply didn't evolve to think about things this small. Our ancestors needed to understand the size of fruits and animals and other humans, things measured in centimeters and meters. They never needed to think about billions of meters, so our intuition fails us completely when we try. When we look at something like a wooden table, we see a flat, solid surface. We see brown color, we see texture. Maybe we see the grain of the wood running through it. Darker lines and lighter areas creating patterns. We can run our fingers across it and feel the smoothness, or perhaps a slight roughness. If we press down on it, it feels hard, unyielding. The table seems to be exactly what it appears to be, a solid object, continuous and unbroken, made of something called wood that has always been wood and will always be wood. But if we could zoom in, really zoom in, past what our eyes can see, past what regular microscopes can show us, we would discover something astonishing. This table is not solid at all. It's not even close to solid. It's made of molecules, which are groups of atoms bonded together. These molecules are made of atoms, which are themselves made of even tinier particles, all surrounded by vast amounts of space. If you could somehow see the table at the atomic level, it would look more like a vast, swirling cloud of tiny particles, most of them not even touching each other, all vibrating and moving in constant motion. The solid, stable table would reveal itself to be a temporary arrangement of particles that are mostly just empty space with occasional specks of matter. The strange thing is, we can't actually see atoms the way we see a dog or a tree or a friend's face. Atoms are so unbelievably small that light itself, the very thing that lets us see everything else, is far too large to bounce off them in any useful way. This is such an important point that it's worth exploring in more detail, because it helps us understand just how different the atomic world is from the world we experience every day. You see, when you look at something, what's really happening is that light, which travels in waves, bounces off the object and enters your eyes. Your eyes detect this reflected light, and your brain interprets the patterns of light and dark, the colors and shapes, to create an image. For this to work, the wavelength of the light, the distance from one wave peak to the next, needs to be smaller than, about the same size as the object you're looking at. If the wavelength is much larger than the object, the light just flows around it without really interacting with it, like ocean waves flowing past a tiny pebble without being disturbed. The wavelength of visible light, the light that enters our eyes and lets us see the world, ranges from about 390 to 700 nanometers. Blue light has a wavelength of around 450 nanometers. Red light has a wavelength of around 700 nanometers. These are already incredibly small distances, much smaller than anything we can see without magnification. But a typical atom is only about 1/10 of a nanometer across. That means light waves are 4,000 to 7,000 times bigger than the atoms themselves. It would be like trying to examine a grain of rice using your hands while wearing boxing gloves the size of cars. The tool is simply too big for the job. Imagine trying to feel the shape of a tiny pebble while wearing thick winter gloves, the kind you wear in freezing weather with multiple layers of insulation. You could touch the pebble, you could move it around, you could tell approximately where it is, but you could never really feel its exact shape or surface texture. You'd know something was there, but the details would be completely hidden from you. That's what trying to see atoms with ordinary light is like. The light is simply too big, too clumsy, too coarse a tool to reveal the details we want to see. So, if we can't see atoms with light, and we can't see them with our eyes, how do we know atoms exist at all? How do we know their size, their shape, their behavior? if we can't see them directly? How do we know we're not just making them up, inventing tiny particles to explain things we don't understand? This is one of the beautiful stories of science. A story that shows how human cleverness can overcome the limitations of human senses. A story of brilliant thinking, careful experiments, and tools that let us explore the invisible. For thousands of years, people wondered what would happen if you kept cutting something smaller and smaller. If you cut an apple in half, then cut that half in half, then kept going and going and going, would you eventually reach a point where you couldn't cut any more? Would you find some fundamental, indivisible piece? Or could you keep cutting forever, finding smaller and smaller pieces without end? The ancient Greek philosopher Democritus, living around 400 years before the Common Era, thought deeply about this question. He was a man who loved to think about the nature of reality, about what things are really made of beneath their surface appearance. He proposed that everything, absolutely everything in the world, is made of tiny, uncuttable particles he called atomos, which means indivisible in Greek. According to Democritus, if you could keep cutting something smaller and smaller, you would eventually reach these atoms, and you couldn't cut them any further because they were the fundamental pieces from which everything else was built. Different types of atoms, with different shapes and sizes, combined in different ways to create all the different substances we see in the world. It was a beautiful idea, elegant and logical, born of pure thought and reasoning. Democritus had no experiments to back it up, no measurements to support it. He couldn't see atoms or detect them. He simply thought that the idea made sense, that it explained how change and transformation could happen in the world while still maintaining some fundamental constancy. It was philosophy, not science, but it was remarkably close to the truth. For more than 2,000 years, the idea of atoms remained just that, an idea, a philosophical speculation. Some people believed in them, finding the concept logical and appealing. Others rejected them, preferring different explanations for how matter worked. There was no way to settle the question because there was no way to test it. Science needs evidence, solid facts that can be measured and verified, and atoms were far too small to provide any. They remained in the realm of theory, untouchable and unprovable. But then, in the early 1900s, something remarkable happened. A scientist named Albert Einstein, yes, that Einstein, the one with the wild hair and the brilliant mind and the famous equation about energy and mass, published a paper that finally proved atoms were real. And he did this not by somehow making them visible, but by studying something as simple and ordinary as dust particles floating in water. The story starts with a curious observation that scientists had noticed for decades. When you look at dust particles in a beam of sunlight streaming through a window, or when you look at pollen grains floating on the surface of water under a microscope, they don't sit still. They jitter and jump and move in random, jerky ways, like they're being constantly bumped and jostled by invisible hands. This movement is called Brownian motion, named after a botanist named Robert Brown, who first carefully documented it in the 1820s while looking at pollen grains under a microscope and wondering why they wouldn't stay still. At first, Brown thought the pollen might be alive, that the motion was somehow a sign of life. But he saw the same movement with dust from rocks, with tiny particles of completely non-living matter. The jittering had nothing to do with life. It was just something that tiny particles did when suspended in water or air, and nobody knew why. For a long time, no one could explain this strange behavior. Why would particles move randomly like that? What was pushing them? There was no wind underwater, no current that would create such erratic motion. The movement seemed to come from nowhere, and it never stopped. As long as you watched, the particles kept dancing their jerky little dance, moving this way and that, with no pattern or purpose. Einstein realized that the jittering could be explained if water itself was made of countless tiny particles, atoms and molecules, constantly moving and bumping into things. Water, he proposed, wasn't a continuous, smooth substance. It was a collection of molecules, each one moving randomly at high speed due to heat. These water molecules were far too small to see, but they were there, billions upon billions of them, colliding with each other and with anything else in the water millions of times per second. When these invisible water molecules bumped into a much larger dust grain, they would push it slightly. Most of the time, the dust grain would be hit by about the same number of molecules on all sides, so the pushes would balance out and the grain wouldn't move much. But due to random chance, sometimes a few more molecules would hit one side than the other. When that happened, the dust grain would lurch slightly in that direction. A moment later, more molecules might hit from a different direction, and the grain would lurch that way instead. All these random bumps from invisible molecules would create the jerky, random motion that Brown had observed. Einstein worked out the mathematics of how this should happen. He calculated how large the random movements should be based on the temperature of the water, the size of the dust particles, and the size and mass of the water molecules doing the bumping. His equations predicted exactly how fast the particles should move, how far they should travel in a given amount of time, and how this should change with temperature. Everything depended on the size and mass of individual atoms and molecules. Other scientists, particularly a French physicist named Jean Perrin, performed careful measurements of dust particles under microscopes, tracking their movements precisely and comparing the observations to Einstein's predictions. The match was perfect. The mathematics worked exactly as Einstein said it should. And by measuring how the dust particles moved, Perrin could calculate the size and mass of the individual water molecules causing the bumps. The numbers came out consistent every time, giving the same answer regardless of which type of particle was tracked or how the experiment was set up. It was no longer possible to reasonably doubt that atoms were real. The invisible had finally been proven through its effects on the visible. Atoms and molecules were not philosophical speculation. They were real physical objects that followed mathematical laws and could be measured indirectly through their effects. Einstein's work on Brownian motion, published in 1905, the same miraculous year when he published his theory of special relativity and his explanation of the photoelectric effect, finally settled a question that had puzzled humanity for over 2,000 years. Atoms exist. They're real. And we can study them scientifically. Now that we know atoms exist, now that we've established they're real physical objects that can be studied and measured, let's try to understand just how extraordinarily small they really are. Because small doesn't quite capture it. Atoms aren't just small the way a seed is small compared to a tree, or the way a mouse is small compared to an elephant. Atoms are small in a way that's almost impossible for our minds to grasp. Small on a scale so different from our everyday experience that we have to use comparison after comparison just to begin to appreciate it. A typical atom is about 1/10 of a nanometer in diameter. Remember, a nanometer is 1/1000th of a meter. So an atom is about 1/10 billionth of a meter across. Let's try to put that in terms we can imagine, even though our brains will struggle with the scale. Let's pile up comparison after comparison until the incredible smallness starts to sink in. Think about a single strand of human hair. Pick one off your head and hold it up to the light. It feels thin, delicate, almost invisible when you look at it edge on. That single hair, so thin you can barely see it, is about 50,000 to 100,000 nanometers wide. Different people have different thickness hair, but 50,000 to 100,000 nanometers is a typical range. An atom, remember, is 1/10 of a nanometer. This means that if you could somehow line up atoms side by side across the width of a human hair, you would fit about 500,000 to 1 million atoms across. 500,000 to 1 million tiny particles, all lined up touching edge to edge, just to span something as thin as a hair. And remember, we're talking about the width of the hair, not its length. The hair itself contains far, far more atoms than that. Let's try another comparison, something else you interact with every day. Think about a sheet of paper, the kind you might write a letter on or print a page from your computer. Hold it between your fingers and feel how thin it is. You can bend it, fold it, crease it easily. A typical sheet of paper is about 75,000 nanometers thick, or about 0.075 millimeters. If you could somehow stack atoms on top of each other to reach that thickness, carefully placing one atom atop another like microscopic building blocks, you would need about 750,000 atoms. 750,000 atoms stacked precisely to equal something as thin as a single page. And again, that's just the thickness. The total number of atoms in a whole sheet of paper is incomprehensibly larger. Or consider this comparison, which really helps show the scale. Take a tiny grain of sand, so small you can barely see it, just a speck on your fingertip. You know how small that is. You've probably had grains of sand stick to your skin after a day at the beach, and you've brushed them away without thinking. Each grain is already almost invisible, barely noticeable. But if we could somehow magnify that grain of sand, make it grow and grow and grow until it was as large as the entire Earth, our whole planet, then the atoms inside it would be about the size of a car or a small bus. That's the scale we're talking about. The relationship between a grain of sand and the Earth, something like 8,000 miles of difference, is similar to the relationship between an atom and that tiny grain of sand. The jumps in scale are almost identical, but in opposite directions. Here's another way to think about it, using something wet this time. Imagine a single drop of water, the kind that forms at the tip of your finger when you've just washed your hands. One small drop, barely enough to feel the weight of. That drop contains approximately 1 sextillion water molecules. That's a 1 followed by 21 zeros, 1,000 billion molecules in a single drop. Each molecule is made of 3 atoms, 2 hydrogen and 1 oxygen, so that's 3 sextillion atoms in total. If you tried to count them, assigning one number to each atom, counting 1 per second without pause, without sleeping or eating or resting, it would take you about 95 billion years to finish counting the atoms in a single drop of water. That's nearly 7 times the current age of the universe. 1 drop. 7 universe lifetimes to count it. If you took all the atoms in that single drop of water and somehow lined them up in a row, a perfect straight line stretching across space, that row would stretch from Earth to the Sun and back, twice. Actually, probably more than twice. The Earth is about 93 million miles from the Sun, and a round trip would be 186 million miles. Atoms are about 1/10 of a nanometer wide, and there are about 25 million nanometers in an inch. Doing the math carefully, that line of atoms from 1 drop of water would reach the Sun and back many times over. That's how many atoms we're talking about, and that's how small each one is. Scientists who want to be very precise, who work with atoms professionally in laboratories and research centers, often measure atoms in something called angstroms. An angstrom is 1/10 of a nanometer, or 1/10 billionth of a meter. It's named after a Swedish physicist named Anders Jonas Ångström, who studied light and spectroscopy in the 1800s. Most atoms are between 1 and 5 angstroms in diameter. A hydrogen atom, the simplest and smallest atom in existence, has a diameter of about 1.06 angstroms, or just over 1/10 of a nanometer. Larger atoms, like gold or lead, might be 4 or 5 angstroms across, but even these large atoms are still incredibly tiny by any human standard. To give you one more comparison, one more way to try to grasp this incredible smallness, imagine a full stop, a period at the end of a sentence. Look at one right now, at the end of this sentence or the next. You can see it easily. It's small but clearly visible, just a tiny dot of ink or pixels on the page or screen. A full stop is usually about 3 millimeters wide, or 3 million nanometers. The width of a hydrogen atom is about 0.1 nanometers. This means you could fit about 30 million hydrogen atoms across the diameter of that full stop. 30 million, all lined up edge to edge, just across a tiny dot of ink. And that's just in one direction, just across the diameter. If we filled the entire area of the period with hydrogen atoms, packed them in efficiently like tiny spheres filling a space, we'd need nearly 1 trillion atoms. The numbers become so large they lose meaning, become just abstract symbols that our minds can't really process. These numbers are so large, so far beyond our everyday experience, that they stop feeling real after a while. Our brains evolved to think about things we can see and touch, things measured in centimeters and meters, not things measured in billionths of meters or counted in sextillions. So if these comparisons make your mind feel a little dizzy, if you find yourself unable to really picture what we're talking about, that's completely normal. You're trying to imagine something that evolution never prepared you to understand. Your ancestors needed to judge the size of a deer to hunt, the distance to a tree for shelter, the height they could climb without falling. They never needed to think about billionths of meters, so your brain doesn't have the built-in tools to handle it naturally. But that's okay. That's actually kind of beautiful in a way. Even scientists who work with atoms every day, who do calculations involving atomic sizes constantly, who have devoted their entire careers to studying these tiny particles, even they can't really visualize atoms in the way they can visualize a tree or a building or a person's face. They just learn to work with the numbers, learn to trust what the mathematics tells them, and develop an intuition based on equations rather than direct perception. They learn to think in scales they can't actually picture, and somehow, amazingly, it works. They can predict how atoms will behave, how they'll bond together, what properties materials will have, all without ever really seeing what they're working with in any conventional sense. Now let's take our journey deeper. Let's not just think about how small an atom is from the outside, looking at its overall size, but let's explore what's inside an atom. Because atoms themselves are not solid little balls. They're not tiny marbles or grains of dust. They're more like tiny universes, with their own structure, their own parts, their own strange rules and behaviors that don't apply to anything in our everyday world. Every atom, no matter what element it is, no matter how large or small, has a center called the nucleus. The nucleus is unimaginably tiny compared to the atom as a whole, but it contains almost all of the atom's mass, almost all of its weight. In fact, the nucleus makes up more than 99.95% of the atom's mass, even though it only occupies about 1/1,000,000,000th of the atom's volume. Think about that for a moment. Nearly all the mass, crammed into 1/1,000,000th of the space. The density is extraordinary, far beyond anything we experience in our daily lives. To understand this incredible concentration of mass, let's use another comparison. Imagine you could expand a single atom, make it grow larger and larger, until it was the size of a large sports stadium, like a football stadium or a baseball park. If the atom were that enormous, if the electrons orbited at the distant outer walls, and the whole structure was stadium-sized, then the nucleus at the very center would be about the size of a small pea, sitting right in the middle of the field. Maybe a marble, if we're being generous. Everything else, all that enormous space filling the rest of the stadium, all the seats and aisles and air and open space, all the way from the center field out to the distant walls, would be where the electrons live in their probabilistic clouds. But we'll come back to the electrons in a moment. First, let's focus on that pea, that marble, that tiny nucleus sitting at the heart of everything. This nucleus, this tiny seed at the center of our stadium-sized atom, is made of even smaller particles called protons and neutrons. Together, protons and neutrons are called nucleons, a name that simply means particles in the nucleus. They're held together by the strongest force in nature, appropriately called the strong nuclear force. This force is incredibly powerful at very short ranges, powerful enough to overcome the electrical repulsion between protons and hold the nucleus together. Without the strong nuclear force, the nucleus would fly apart instantly, torn apart by the positive charges of protons, repelling each other with electromagnetic force. Protons carry a positive electrical charge. Each proton has exactly the same amount of positive charge as every other proton in the universe, no matter where it is or when it was created. This charge is one of the fundamental properties of nature, unchanging and constant throughout all of space and all of time. The number of protons in an atom's nucleus is incredibly important, because it determines what element that atom is. This is the defining characteristic, the fingerprint that tells us what we're dealing with. An atom with one proton is hydrogen. Nothing else can be hydrogen, and hydrogen cannot be anything else. An atom with 6 protons is carbon. Always and forever, carbon. An atom with 26 protons is iron. An atom with 79 protons is gold. The number of protons defines the atom's identity completely. Change that number, and you have a different element entirely. This is actually what happens in nuclear reactions, where one element transforms into another by gaining or losing protons. But that's a topic for another time. Neutrons, as their name suggests, are neutral. They have no electrical charge at all. They're slightly heavier than protons, but only by a tiny amount. Neutrons help stabilize the nucleus. Without them, the electrical repulsion between protons would tear most atoms apart. Different versions of the same element can have different numbers of neutrons. These different versions are called isotopes. Carbon, for example, usually has 6 neutrons to go with its 6 protons, but some carbon atoms have 7 neutrons, and some have 8. They're all carbon, but they're slightly different flavors of carbon. How big are protons and neutrons? They're about 1 femtometer across. A femtometer is 1/1,000,000th of a nanometer, or 1/4,000,000,000th of a meter. So if an atom is about 1/10th of a nanometer wide, and the nucleus is about 100,000th the size of the atom, then the protons and neutrons inside the nucleus are about 1/10th the size of the nucleus itself. We're diving into scales so small that even our comparisons start to break down. Now here's something beautiful and strange. Protons and neutrons aren't even the smallest things. They're actually made of even tinier particles called quarks. Each proton is made of 2 up quarks and 1 down quark. Each neutron is made of 1 up quark and 2 down quarks. Quarks are held together by particles called gluons, which carry the strong nuclear force between them. Quarks are so small that scientists have never been able to measure their size directly. As far as we can tell, they might be point-like particles with no size at all, or they might be smaller than anything we can currently measure. When scientists at particle accelerators slam electrons into protons at incredibly high energies, the electrons seem to pass right through most of the proton, only occasionally hitting something hard, a quark. This tells us that even protons and neutrons, tiny as they are mostly empty space with a few quarks inside. So inside each atom, there's a nucleus. Inside the nucleus, there are protons and neutrons. Inside the protons and neutrons, there are quarks. Each level is incredibly smaller than the one before. It's smallness nested inside smallness, like a set of boxes where each box contains another box 100,000 times smaller, and so on, down and down into the heart of matter. Now let's return to that stadium-sized atom we imagined, with its pea-sized nucleus at the center. What about all that empty space? What's happening in the rest of the stadium? This is where the electrons live. Electrons are fundamental particles, meaning as far as we know, they're not made of anything smaller. They're just electrons, pure and simple. Each electron carries a negative electrical charge that exactly balances the positive charge of a proton. If an atom has 6 protons in its nucleus, it will normally have 6 electrons surrounding that nucleus, keeping the atom electrically neutral overall. Electrons are incredibly light. A single electron has only about 1/1836 the mass of a proton. Despite their tiny mass, electrons take up most of the space that we think of as the atom. Or rather, they occupy a cloud of probability around the nucleus, a region where they're likely to be found if we were to look for them. Here's where things get wonderfully strange, and this is one of the most beautiful mysteries of the quantum world. Electrons don't orbit the nucleus the way planets orbit the sun. For a long time, people thought they did. Early pictures of atoms showed them like tiny solar systems, with electrons as little balls following circular paths around the nucleus like miniature Earths and Jupiters. But that's not how it works. Electrons don't have specific paths. Instead, they exist in what scientists call probability clouds or orbitals. These clouds represent all the places an electron might be at any given moment. Until you actually measure where an electron is, it doesn't have a definite position. It exists as a spread-out wave of probability, occupying many places at once in a fuzzy, indefinite way. This isn't because electrons are moving so fast we can't track them. It's something more fundamental. At the quantum level, particles simply don't have definite positions until they're measured. An electron around an atom is better thought of as a cloud of maybe here, maybe there, rather than as a tiny ball in a specific location. These electron clouds have different shapes depending on their energy level. Some are spherical, like fuzzy balls surrounding the nucleus. Others are shaped like dumbbells or even more complex forms. Electrons in higher energy levels occupy clouds that are farther from the nucleus and more complex in shape. But no matter their shape, these clouds represent the space where the electron is likely to be, not a path it follows. The size of these electron clouds is what gives an atom its size. When we say an atom is about 1/10 of a nanometer across, we're really talking about the size of its outermost electron cloud. The electrons themselves, like quarks, might be point-like particles with no measurable size. Or they might be incredibly tiny, smaller than anything we can currently detect. What we measure as the atom's size is really the region where its electrons have a significant probability of being found. Now we arrive at something that sounds paradoxical, something that seems impossible, but which is absolutely, verifiably true. Something that has confused and amazed people ever since they first learned about atomic structure. Atoms are almost entirely empty space. The nucleus, as we discussed, is extraordinarily tiny compared to the overall size of the atom. If the atom is a stadium, the nucleus is a pea. The electrons, if they have any size at all, are far tinier still, perhaps like grains of dust floating in all that stadium space. Our stadium comparison, we have a pea-sized nucleus and some electrons no bigger than specks of dust, all occupying a space the size of a massive football stadium. The rest, the vast majority of the volume, is just emptiness, or so it seems. Think about what this means for your body, for everything solid you interact with. If you could somehow remove all the empty space from all the atoms in your body, if you could push all the protons and neutrons and electrons together with absolutely no space between them, compacting everything down into pure matter with no gaps, your entire body would be compressed into a speck smaller than a grain of salt. All of you, everything that makes you who you are physically, all the bones and muscles and organs and skin and hair and fingernails, all of it would fit into something you could barely see. It sounds utterly impossible, absurd even, like something from a science fiction story rather than actual reality. But the mathematics is clear, and the physics supports it completely. Let's extend this thought even further, make it even more dramatic. If we took every human who has ever lived on Earth, all 100 billion people or so who have walked this planet throughout history, from the very first humans hundreds of thousands of years ago to everyone alive today, and if we removed all the empty space from all the atoms in all those bodies, all of humanity throughout history would fit into a volume about the size of a sugar cube. 100 billion people, centuries and centuries of human existence, reduced to a sugar cube when you remove the emptiness. All the mass is there, mind you. That sugar cube would weigh as much as all those humans combined, many trillions of tons. But the volume would be sugar cube-sized, because we removed all the empty space that makes atoms so roomy. This brings us to a profound question, perhaps the most puzzling aspect of this whole discussion. If atoms are mostly empty space, if there's almost nothing there, why can't we walk through walls? Why can't our hand pass through a table? Why does matter feel solid at all? When you press your hand against a wall, why doesn't it simply pass through, like a ghost walking through a door? The wall's atoms are mostly empty. Your hand's atoms are mostly empty. So why can't the empty spaces simply overlap? The answer is both simple and profound, and it reveals something fundamental about the nature of reality. While atoms might be mostly empty in terms of matter, in terms of actual particles taking up space, they're not empty in terms of forces and fields. Those electron clouds, those fuzzy regions of probability where electrons might be found, are regions of intense electrical force. And here's the key point. Electrons are negatively charged, and negative charges strongly, powerfully, dramatically repel other negative charges. This repulsion is one of the fundamental forces of nature, and it's incredibly strong at short distances. When you place your hand on a table, here's what's really happening at the atomic level. The electron clouds in the atoms of your hand get very, very close to the electron clouds in the atoms of the table. As they approach each other, as the distance between them decreases, the negative charges in your hand's electrons start to repel the negative charges in the table's electrons. This repulsion grows stronger and stronger the closer they get. Long before your hand's atoms could actually touch the table's atoms, long before the nuclei could get anywhere near each other, the electrical repulsion becomes so incredibly strong that your hand simply cannot push any further. The electromagnetic force, one of the four fundamental forces of nature, creates an impenetrable barrier. The table feels solid, not because it's full of matter in every cubic nanometer, but because it's full of repelling electrical forces that won't let other electrons approach. In a very real and literal way, you've never actually touched anything in your entire life. When you touch your face, when you shake someone's hand, when you pet a dog, when you feel the softness of a pillow or the hardness of a rock, your atoms and their atoms never actually make contact. They get very, very close, perhaps within a nanometer or even less, close enough that the electrical forces become very strong. But there's always a tiny gap, a fraction of a nanometer perhaps, between your atoms and theirs. What you feel as touch, what your brain interprets as physical contact, is actually the electrical repulsion between electron clouds. You're feeling electromagnetic force, not physical contact. You're sensing fields interacting with fields, charges pushing against charges, forces meeting forces, but never matter touching matter, not in the simple, direct way we imagine. This is why objects feel solid, even though they're mostly empty. The forces filling that empty space are strong enough, real enough, that they might as well be solid walls. In fact, they're more effective than solid walls because they can never be breached at normal energies. You can break through a concrete wall if you hit it hard enough, but you cannot force one electron cloud through another through normal means. The electromagnetic repulsion will always win. So atoms are empty, but that emptiness is filled with fields and forces and interactions. The electron clouds aren't just empty space with an occasional electron passing through like a lonely traveler in a desert. They're regions where the electron has a high probability of being detected, and they're regions permeated by electrical fields that strongly affect other atoms and particles nearby. The emptiness is full in its own strange quantum mechanical way. Empty of matter, but full of potential, full of force, full of electromagnetic interactions that govern how atoms relate to each other and create the world of stuff we experience every day. Modern physics tells us that empty space itself might not be truly empty at all. According to quantum field theory, even a perfect vacuum, a region with no atoms, no electrons, no particles of any kind, still contains energy. Tiny particles pop into existence and disappear again in fractions of a second, borrowing energy from the vacuum itself. The vacuum bubbles and seethes with activity at the quantum level. Space, it turns out, is never truly empty, even when there's nothing in it. You might wonder, if atoms are so impossibly small, how do we know so much about them? How do we know about the nucleus, the electrons, the quarks? How can we study something we can never directly see? The answer lies in clever tools and indirect measurements. While we can't use ordinary microscopes to see atoms, scientists have developed extraordinary instruments that let us probe the atomic world in other ways. One of the most important tools is called a scanning tunneling microscope, or STM for short. This remarkable device was invented in 1981 by scientists Gerd Binnig and Heinrich Rohrer, who won the Nobel Prize for their work. An STM doesn't use light at all. Instead, it uses an incredibly sharp metal needle, so sharp that the tip is only a single atom wide. The needle is brought incredibly close to the surface being studied, so close that it's only a nanometer or so away. At this distance, something called quantum tunneling allows electrons to jump from the surface to the needle, creating a tiny electrical current. By measuring how this current changes as the needle moves across the surface, scientists can create a map of where individual atoms are located. With an STM, scientists can do more than just see atoms. They can actually move them, one at a time, pushing individual atoms across a surface to arrange them in patterns. In 1989, scientists at IBM spelled out the company's logo using 35 individual xenon atoms, each one carefully positioned. It was the smallest logo ever created, a demonstration that we can not only observe the atomic world, but manipulate it. Another tool, called an atomic force microscope, or AFM, works in a similar way, but can be used on a wider variety of materials. It measures the tiny forces between a sharp tip and the surface below, building up a picture of atomic structures through touch rather than tunneling current. For studying what's inside atoms, scientists use particle accelerators. These are enormous machines that speed up particles like electrons or protons to nearly the speed of light, then smash them into target atoms. By carefully measuring what comes out of these collisions and which directions the particles scatter, scientists can figure out what must be inside the atoms to produce those particular results. It's like throwing balls at something in the dark and figuring out its shape by how the balls bounce back. Electron microscopes, which use beams of electrons instead of light, can create images with resolutions down to about 1/10 of a nanometer, small enough to resolve individual atoms under the right conditions. The electrons, being much smaller in wavelength than visible light, can reveal details that ordinary microscopes cannot. Through all these techniques and many others, scientists have built up an incredibly detailed picture of atoms and their structure. We know the sizes, masses, and charges of protons, neutrons, and electrons with extraordinary precision. We know how atoms bond together to form molecules. We know how electrons arrange themselves in clouds around nuclei. We understand the forces that hold matter together and the quantum rules that govern atomic behavior. All of this knowledge came from asking questions about things we couldn't see, then developing clever ways to gather evidence and piece together answers. It's one of the great triumphs of human curiosity and ingenuity. Not all atoms are the same, of course. In fact, there are many different kinds of atoms, each with its own specific properties. As we mentioned earlier, what makes atoms different from each other is the number of protons in their nucleus. The simplest atom is hydrogen, with just one proton in its nucleus and one electron surrounding it. Most hydrogen atoms have no neutrons at all, making hydrogen the lightest element. Hydrogen is incredibly common in the universe. It makes up about 75% of all the matter we can see in stars, galaxies, and clouds of gas between stars. Next comes helium, with 2 protons and usually 2 neutrons. Helium is the gas that makes balloons float and makes voices sound funny when you breathe it in. It's the second most common element in the universe. Then lithium with 3 protons, beryllium with 4, boron with 5, and carbon with 6. Carbon is particularly special because it can bond with many other atoms in many different ways, forming long chains and complex structures. This flexibility makes carbon the foundation of all life on Earth. Every living thing, from bacteria to blue whales, from grass to giant redwood trees, is built from carbon-based molecules. As we continue adding protons, we get nitrogen with 7 protons, oxygen with 8, and so on. Each element has unique properties determined by its number of protons. Gold has 79 protons, which gives it its distinctive yellow color and its resistance to tarnishing. Iron has 26 protons, and its atoms can align their magnetic properties, which is why iron is magnetic. Silicon has 14 protons, and its properties make it perfect for use in computer chips. Scientists have discovered or created 118 different elements so far. Each one occupies a specific spot on the periodic table, organized by its number of protons. The periodic table is like a map of matter, showing how elements are related to each other and predicting their properties based on their position. Some elements are stable, meaning their atoms can exist unchanged for essentially forever. Others are unstable, meaning they gradually break down through a process called radioactive decay, transforming into different elements over time. Uranium, with 92 protons, is a famous example of an unstable element. Its atoms slowly break apart, releasing energy and particles, eventually transforming into lead over millions of years. The atoms in your body, the carbon and oxygen and nitrogen and iron and all the others, were not created on Earth. They were forged inside ancient stars. Billions of years ago, stars much larger than our Sun burned their hydrogen fuel, creating helium. Then they burned helium, creating carbon and oxygen. Heavier elements formed in layers deep inside massive stars. When these stars eventually exploded in supernovae, they scattered these elements across space. Clouds of this enriched gas eventually collapsed to form new stars and planets, including our Sun and Earth. So the atoms in your hand, the iron in your blood that carries oxygen, the calcium in your bones, the carbon in your DNA, all of it was once inside a star. You are made of stardust, not metaphorically, but literally. The atoms that make you existed in stars that ended their lives long before our solar system even formed. Those atoms traveled across light years of space, gathered together through gravity, and eventually, after billions of years, found their way into you. Every atom in your body has a cosmic history spanning the lifetime of the universe. Atoms are never still, never at rest, never truly quiet. Even in solid objects, in a wooden chair or a steel beam or a diamond crystal, the atoms are constantly moving, vibrating in place like tiny bells that never stop ringing. Temperature is really just a measure of how fast atoms are moving. In a hot object, atoms vibrate more vigorously. In a cold object, they vibrate more slowly. Even at the coldest temperature theoretically possible, called absolute zero, which is minus 273.15 degrees Celsius, atoms would still have some motion due to quantum effects. They can never be completely still. In gases, atoms and molecules zip around freely, bouncing off each other and the walls of their container thousands of times per second. Air molecules at room temperature move at speeds of around 500 meters per second, faster than the speed of sound. When you breathe, you're inhaling a chaotic swarm of nitrogen and oxygen molecules, all flying in random directions, constantly colliding and bouncing apart. In liquids, atoms are closer together and move more slowly, sliding past each other rather than flying freely. They're held loosely by attractive forces between atoms, but these forces aren't strong enough to lock the atoms in place. This is why liquids can flow and take the shape of their container, but don't expand to fill all available space like gases do. In solids, atoms are locked into fixed positions relative to each other, held by strong bonds that won't let them move away. But even here, they vibrate, shaking back and forth around their equilibrium positions. This vibration is what we measure as temperature. When you heat a solid enough, the atoms vibrate so violently that the bonds between them break and the solid melts into a liquid. When atoms collide, they bounce off each other elastically, like perfectly springy balls. They don't get damaged or worn down by countless collisions. An oxygen atom that's been bouncing around in Earth's atmosphere for millions of years is identical to an oxygen atom that was just created in a star somewhere across the galaxy. Atoms don't age, don't wear out, don't get tired. They're essentially eternal, at least the stable ones. The number of atoms in even small amounts of matter is staggering beyond imagination. A single drop of water, about 20 little drops like you might drip from a medicine dropper, contains approximately 1.5 sextillion molecules. That's 15 followed by 21 zeros. If you could count one molecule per second, it would take you 500 trillion years to count them all, many thousands of times longer than the current age of the universe. A mole, which is a standard unit in chemistry, contains about 602 sextillion particles. This number, called Avogadro's number, is so large that if you had a mole of unpopped popcorn kernels, you could cover the entire United States with a layer of popcorn about 9 miles deep. That's how many atoms are in just 18 grams of water, which is barely more than a tablespoon. Everything around you, everything you can see or touch or taste or smell is made of atoms. The screen or paper you might be looking at, the air you're breathing, the bed or chair you're sitting on, all made of countless atoms arranged in specific patterns. When atoms bond together, they create molecules. A water molecule is 2 hydrogen atoms bonded to 1 oxygen atom. A molecule of sugar has 45 atoms, 22 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms, all connected in a specific arrangement that gives sugar its sweet taste. DNA molecules, which carry genetic information in all living things, can contain millions of atoms arranged in long, twisted chains. The properties of materials depend entirely on how their atoms are arranged, and this is one of the most beautiful and important insights of modern chemistry and materials science. Diamond and graphite are both made of pure carbon, nothing else. Every single atom in both materials is carbon, with 6 protons, 6 neutrons, typically, and 6 electrons. They're chemically identical at the atomic level. But in diamond, each carbon atom bonds to 4 neighbors in a rigid 3-dimensional network, creating the hardest natural material known. The atoms are locked in place so firmly, the bonds are so strong, that diamond can scratch almost anything else. This same arrangement also makes diamond transparent, allowing light to pass through while bending it beautifully, which is why diamonds sparkle so brilliantly when cut properly. In graphite, the same carbon atoms bond in flat sheets that slide easily past each other, making graphite soft and slippery, perfect for pencil leads and lubricants. When you write with a pencil, you're actually leaving layers of graphite atoms on the paper, sheets sliding off the pencil tip. Same atoms, different arrangement, completely different properties. This is the power of structure, of how we organize matter at the atomic level. Salt crystals, the kind you might sprinkle on your food to add flavor, are made of sodium and chlorine atoms arranged in a precise cubic pattern, a perfect geometric lattice. Each sodium atom is surrounded by 6 chlorine atoms, positioned at the corners of an octahedron, and each chlorine atom is surrounded by 6 sodium atoms in the same way. This pattern repeats on and on in all directions, creating a perfect geometric crystal. When you look at a grain of salt with a magnifying glass and see its cubic shape, its flat faces and sharp edges, you're seeing the atomic structure made visible on a larger scale. The visible shape of the salt grain reflects the cubic arrangement of atoms inside, structure repeating at every scale from nanometers to millimeters. Metals are fascinating because they're collections of atoms where the electrons can move freely from one atom to another, not locked to any particular nucleus, but flowing through the entire material like a sea. This sea of mobile electrons is what makes metals good at conducting electricity and heat, and what gives them their characteristic shininess, their lustrous metallic appearance. When light hits a metal surface, the free electrons absorb the light energy and immediately re-emit it, creating the mirror-like reflection we associate with metallic surfaces. The electrons act like tiny antennas, catching light waves and broadcasting them back out. This is why polished metals look so shiny, why they make good mirrors. In your own body, atoms are arranged in staggeringly complex ways to create life, to create consciousness, to create you. The DNA in your cells, the long molecules that contain your genetic information, is made of about 3 billion pairs of atoms, arranged in a specific sequence that contains all the instructions for building you, for determining your eye color and height, and countless other characteristics. Every cell in your body contains a complete copy of this instruction manual, though different cells read different parts of it. Proteins, the molecular machines that do most of the work in cells, are chains of thousands of atoms folded into precise three-dimensional shapes that determine their function. Some proteins transport oxygen through your bloodstream. Others digest the food you eat. Still, others fight infections, repair damage, or send signals between cells. Each protein is a carefully arranged collection of atoms doing a specific job. Enzymes, which are a type of protein, can grab other molecules and rearrange their atoms, making and breaking chemical bonds with extraordinary precision and speed. An enzyme might process thousands of molecules per second, cutting them apart or stitching them together with perfect accuracy, never making a mistake. They're like incredibly skilled craftspeople working at the molecular level, assembling and disassembling atomic structures. Your body contains tens of thousands of different types of enzymes, each one specialized for a specific task, each one a different arrangement of the same basic carbon, hydrogen, nitrogen, oxygen, and sulfur atoms. Your brain contains about 86 billion nerve cells, and each of those cells contains trillions upon trillions of atoms, all working together in coordinated harmony to generate your thoughts, memories, emotions, and consciousness. Right now, as you read or listen to these words, atoms in your brain are moving, electrons are flowing through neural pathways, and molecules are changing their structure, creating the physical basis for your experience of understanding what atoms are. The fact that atoms can organize themselves into a structure capable of understanding atoms is perhaps the most remarkable thing of all. Matter becoming aware of itself through sheer complexity of arrangement. We've talked about how small atoms are, we've explored their structure and behavior, but we haven't fully explored how strange they are. At the atomic scale, the rules that govern everyday objects no longer apply. Welcome to the world of quantum mechanics, where reality behaves in ways that defy common sense. One of the fundamental principles of quantum mechanics is called the uncertainty principle, discovered by Werner Heisenberg in 1927. This principle states that you cannot simultaneously know both the exact position and the exact momentum of a particle, like an electron. The more precisely you know where it is, the less precisely you can know where it's going, and vice versa. This isn't due to imperfect measurements or clumsy instruments. It's a fundamental feature of reality at the quantum scale. Particles simply don't have definite positions and momentums at the same time. Before you measure them, they exist in a fuzzy state of possibility, neither here nor there, but somehow both. Another quantum property is called superposition. An electron in an atom doesn't orbit in one specific path or exist in one specific location. Until you measure it, it exists in all its possible states simultaneously. It's in a superposition of being in many places at once, following many paths at once, having many energies at once. Only when you make a measurement does the electron choose one specific state, collapsing from many possibilities into one reality. This sounds like philosophy or magic, but it's experimentally verified. Scientists have demonstrated superposition countless times with photons, electrons, and even larger molecules. The quantum world really does work this way, even though our everyday experience gives us no intuition for it. Particles can also exhibit a property called entanglement. When two particles become entangled, they remain connected in a strange way, even if they're separated by vast distances. Measuring one particle instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance, and was deeply uncomfortable with it. But experiments have confirmed that entanglement is real, and scientists are now using it to develop quantum computers and secure communication systems. At the quantum level, particles also exhibit wave-particle duality. Electrons, protons, and even whole atoms behave like waves in some experiments and like particles in others. They're not really waves, and they're not really particles. They're something else, something that has properties of both, depending on how you choose to observe them. This duality is built into the fundamental nature of matter and energy. Light does the same thing, sometimes acting like a wave, sometimes like a stream of particles called photons. These quantum properties aren't just curiosities, they're essential to how atoms work. Electrons can only occupy certain specific energy levels around an atom because of their wave nature. When an electron jumps from one energy level to another, it absorbs or emits a photon of light with a specific energy. This is why each element produces a unique pattern of colors when heated, a pattern as distinctive as a fingerprint. By analyzing the light from distant stars, astronomers can determine what elements those stars contain, even though the stars are trillions of miles away. Quantum mechanics also explains why atoms are stable. In classical physics, an electron orbiting a nucleus should radiate energy and spiral inward, causing the atom to collapse in a fraction of a second. But quantum mechanics tells us that electrons can't do this. They're confined to specific energy levels, and there's a lowest possible level they can occupy. An electron in this lowest level, called the ground state, has nowhere lower to go. It's stuck there, unable to fall any further. This is why atoms don't collapse, why matter is stable, why you don't suddenly disintegrate into a shower of radiation. Thank you, quantum mechanics. Despite their incredibly tiny size, despite being so small that we need special microscopes and clever indirect methods just to detect them, atoms are the foundation of everything. Understanding atoms has allowed humans to accomplish remarkable things. Modern medicine depends on understanding atoms and molecules. Drugs work by having molecules with specific shapes that fit into receptors on cells, like keys fitting into locks. The shape of the molecule, determined by how its atoms are bonded together, determines what it can do in the body. By understanding atomic structure, scientists can design new medicines to fight illnesses, targeting specific molecular interactions with incredible precision. The entire field of chemistry is really the study of how atoms bond, rearrange, and interact. Every chemical reaction is just atoms changing partners, breaking old bonds and forming new ones. Burning wood, rusting iron, baking bread, digesting food, all these processes are just atoms rearranging themselves into new configurations. Modern technology is built on manipulating matter at the atomic level. The computer chip at the heart of your phone or computer contains transistors, tiny switches that turn current on and off. Modern chips contain billions of these transistors, each one created by precisely arranging atoms of silicon and other elements in specific patterns. The entire chip is built up layer by layer, with features measured in nanometers, just a few atoms wide. We've learned to engineer structures at the atomic scale, creating devices that would have seemed like magic just a few decades ago. Materials science, the field of designing new materials with specific properties, works by arranging atoms in clever ways. Carbon fiber is incredibly strong for its weight, because of how the carbon atoms are bonded together in sheets. Kevlar, used in bulletproof vests, is strong because its molecules are long chains of atoms aligned in parallel, making them incredibly difficult to pull apart. Aerogel, one of the lightest solid materials known, is mostly empty space, with just a sparse network of atoms holding its structure together. Scientists are now working with atoms in even more sophisticated ways. They're building machines at the nanoscale, devices made of just a few hundred or a few thousand atoms, arranged in specific ways. They're creating new materials that don't exist in nature, arranging atoms in patterns that give them properties we can't find anywhere else. They're learning to harness quantum properties for new types of computers that could solve problems impossible for classical computers to tackle. Understanding atoms has also revealed deep truths about the universe itself. By studying how atoms behave at extremely high temperatures and energies, scientists can understand what happened in the first moments after the Big Bang. By examining the atoms in meteorites and moon rocks, they can piece together the history of our solar system. By analyzing the light from distant galaxies, they can study the evolution of the universe over billions of years. As we reach the end of our journey into the microscopic universe, as this gentle exploration of the impossibly small comes to a close, it's worth taking a moment to step back and feel the wonder of it all. To let the full significance of what we've discussed settle softly into your mind. You are made of about 7 billion atoms. That's 7 followed by 27 zeros, a number so large it's almost meaningless. Each of those atoms is impossibly tiny, measured in billionths of meters. Each is mostly empty space, held together by forces we can't see or feel directly. Each has its own structure, its own component parts, its own quantum nature. And yet, arranged in just the right ways, these tiny, simple building blocks create everything. They create mountains and oceans, stars and planets, bacteria and elephants, roses and redwood trees. They create your body, with its complex organs and tissues, its intricate nervous system, its beating heart. They create your brain, with its billions of neurons and trillions of connections, giving rise somehow to your thoughts, your memories, your dreams, your sense of self. The atoms in your body are ancient. The hydrogen atoms in the water you drink were created in the Big Bang, nearly 14 billion years ago. The carbon atoms in your muscles, the calcium in your bones, the iron in your blood, all forged in stars that lived and ended their lives billions of years ago, before the Earth even existed. These atoms have been recycled countless times, used by other organisms, scattered across the world, brought together again by chance and chemistry. The same atoms that make you also make the ground beneath your feet, the air you breathe, the food you eat. You're not separate from the world around you. You're made of it, literally, connected to everything through the fundamental building blocks of matter. Every breath is an exchange of atoms between your body and the atmosphere. Every meal is an incorporation of atoms from plants and animals into your own structure. You're a temporary pattern in the flow of atoms, a brief arrangement that will eventually dissipate and rearrange into new forms. And yet, temporary as you are, you're conscious. You can contemplate these atoms, understand them, wonder about them. A collection of atoms has become aware of its own existence and nature. The universe has organized itself, through you, to study itself. That's perhaps the most remarkable thing of all. Scientists will continue to probe deeper into the nature of matter, asking questions about quarks and the forces between them, about the quantum nature of reality, about whether there might be even smaller layers of structure we haven't discovered yet. There's always more to learn, always deeper mysteries to explore. But for tonight, for this moment, it's enough to know that you're made of atoms. Impossibly tiny, beautifully structured, quantum mechanically strange atoms. That the solid world around you is built from particles too small to see, separated by vast expanses of mostly empty space, held together by invisible forces following mathematical rules we've only recently begun to understand. It's enough to know that you can hold your hand in front of your face and realize that what you see is not solid matter, but a vast collection of tiny universes, each atom a world unto itself, with a dense core and a surrounding cloud of probability. That when you touch anything, you're not really touching it, but feeling the electromagnetic forces between electron clouds. That when you look at the stars, you're seeing light created by atoms fusing together in nuclear reactions. Photons that have traveled across light years to reach your eyes, to be absorbed by atoms in your retina, triggering chemical reactions that your brain interprets as starlight. The microscopic universe is all around you, inside you, making up everything you are and everything you'll ever experience. It's a universe of unimaginable smallness and incredible complexity, of quantum strangeness and mathematical beauty, of forces and fields and particles dancing together to create the world. And now, as we come gently to the end of our journey, as your thoughts perhaps begin to slow and soften like honey dripping from a spoon, as your mind settles like dust motes finding rest after dancing in a beam of sunlight, I want you to know something important. You've done enough thinking for today. You've contemplated impossibly large numbers and impossibly small scales. You've imagined stadiums and grains of sand, hydrogen atoms and carbon chains, nuclei and electron clouds. You've thought about quantum mechanics and forces, about emptiness and fullness, about stardust and structure. Your mind has worked hard tonight, traveling from the world you can see to the world too small for light to reveal. But now it's time to rest. Close your eyes if you haven't already. Let your breathing slow. Feel the weight of your body, which is really just the electromagnetic forces of countless atoms pressing against countless other atoms. Feel the warmth, which is really just the vibration of those atoms, slowing gently as you relax. You're experiencing the atomic world through your own body, even as you drift towards sleep. The atoms in you will continue their endless dance, vibrating, bonding, rearranging, doing their quantum mechanical things, whether you're awake or asleep, whether you're thinking about them or not. They've been dancing for billions of years, and they'll keep dancing long after you're gone, reassembling into new patterns, new structures, new temporary arrangements of matter that will have their own moment in the sun. But right now, in this moment, they're arranged as you, a thinking, feeling, conscious pattern of atoms that can appreciate its own existence, even if just for a little while. And that's beautiful. That's enough. That's more than enough. So rest now, little universe. Let your thoughts dissolve like fog in the morning sun. Let the wonder and the strangeness and the beauty of the atomic world carry you gently toward dreams, toward that strange state where consciousness loosens its grip, and the boundary between you and the rest of reality becomes soft and permeable. The atoms will take care of themselves. They don't need your attention. They've been doing this for 14 billion years without supervision, and they'll continue just fine while you sleep. They'll keep your heart beating, your lungs breathing, your body warm. They're good at what they do. You can trust them. So, let go. Let yourself float on the sea of atoms, part of the great cosmic pattern that creates everything from nothing, that builds complexity from simplicity, that somehow, miraculously, gave rise to you. You're made of stardust, remember? Ancient atoms from dead stars, recycled and rearranged into someone who can understand what atoms are, can marvel at their size, can feel wonder at their structure. You are temporary, but your atoms are nearly eternal. You are small, but you're made of things far smaller. You are conscious, but you're made of parts that are not. You are a beautiful impossibility, a brief coherence in the dance of matter, a temporary stability in the flow of atoms. And right now, in this moment, that's all you need to be. A collection of atoms, feeling sleepy, letting go of the day, sinking into softness and warmth and rest. The microscopic universe continues its endless motion around you and within you, but you can stop thinking about it now. You can simply be it, be part of it. Let yourself dissolve into it. The atoms in your body are home, and they're carrying you home too. To sleep, to rest, to that place where thoughts stop and consciousness dims, and you can just exist for a while without trying to understand anything. Let the atomic world fade from your thoughts. Let the numbers and comparisons and quantum strangeness all drift away like clouds dispersing in a clear sky. You are enough. You've learned enough. You've thought enough. Now rest. Let your atoms be atoms. Let your body be a body. Let your mind become quiet and still, like a lake at dawn with no wind to disturb its surface. Perfect peace. Perfect stillness. Perfect rest. Sleep well, dear listener. Dream of impossibly small things, or dream of nothing at all. Let the universe hold you gently in its vast atomic embrace. You're made of stars, and stars know how to shine, but they also know when to rest. It's your time now. Time to stop shining and start dreaming. The microscopic universe will still be here when you wake, as strange and beautiful as ever. The atoms will still be dancing, still vibrating, still creating the world moment by moment. And you'll still be part of it, a conscious collection of ancient atoms, here for a brief moment to observe and understand and wonder. But for now, wonder can wait. Understanding can wait. Even consciousness can wait. For now, there is only rest, only sleep, only the soft, slow settling of a mind that has traveled far and is finally, gratefully, coming home. Good night. Sleep deep. You are made of atoms, and atoms are made of wonder. And wonder is made of the universe discovering itself. And that's more than enough. That's everything. That's all you need to know as you drift away into dreams. Rest now. You've done enough. Let go. Let sleep come. Let the atomic world carry you gently away. Good night.